today. All right. Well, we better get going. So we have spent the class so far talking about creating music and then some processing of music signals. And now we're moving on to the analysis of music, which is more the area that I've done research in. And today we're talking about rhythm or beat tracking and rhythm tracking, which is a nice classic problem in taking an audio signal and trying to make something higher level, musically relevant out of it. And for me, from a sort of naive, non-expert's point of view, the two essential pieces of music are the notes, the pitch, and the rhythm. And notes kind of make sense because there's this idea of pitch and that we have the mechanisms to perceive pitch, perhaps because of communication and stuff like that. But rhythm it seems to be a little bit less obvious and more mysterious in that music, if we have music that has this regular pulse at around, a couple of hertz, something like that, we're very sensitive to that and we lock onto that and we start tapping our feet or whatever, and it's like it's not simple for me to come up with a evolutionary reason for why that's so important, why we're so good at perceiving that, right? You could imagine creatures that can recognize that there's a sequence of events, but aren't that sensitive to whether there's 10% fluctuation in the event sequence. Whereas when you're listening to rhythm, you actually are pretty sensitive to that. You can tell small percentage differences. And that the things that are going on, they can be fairly complicated. So this is one example. This is actually an example that was introduced to me by Tristan Jahan, who did the audio analysis for the Echo Nest system. And when he was a grad student at MIT, he was working on this music analysis system, and he did some work on rhythm tracking. And he was looking at the problem of trying to detect where the downbeat is, right? So you can have the idea of pulse, what you're going to tap your foot to, but there's also a sense of like where the beginning of the bar is. And he was looking at this kind of cross-culturally, and his argument was that it's not something that's innate, it's something that it's learned. And there's this Brazilian music called maracatu, which he used as an illustration. Actually, this is not it. Let me just play you his example. I don't know if any of you heard maracatu before. That's apparently classic maracatu. And the idea is that if you're a player, you lock into that, you know exactly where it is. But if you're a naive listener, it's a little harder to know exactly what's going on. It's a little bit bewildering. Nonetheless, you can hear that it's rhythmic. Anybody can hear that it's rhythmic, can hear that it's musical. And there are more complicated things that get layered on top. So, it's more of a phenomenon, something that is important in music, but something that has a lot of, we'd like to be able to get out of the music signal for things like, synchronizing music or finding similar pieces of music. So we can think about the problem of trying to extract it automatically. In fact, there's been a series of it's been a lot of work over the last 20 or 30 years of systems that try and pick up beat automatically, automatic foot tapping systems. And there have been some evaluations for this over the past maybe 5 or 6 years. There have been annual evaluations of systems for taking music and outputting foot tap times. which leads to the question, like, how do you evaluate these systems? How do you decide whether one system is better than another? So a while back, some researchers at Philips in the Netherlands, Martin McKinney and Dirk Mullens, tried to gather some ground truth data. And this is beautiful data that they collected. They took, they looked for rhythmically interesting pieces. They made this collection of 30-second excerpts. I think they made over 100, although not all of them have been released. And they were like very varied styles. And some of them were situations where you might expect some ambiguity in what the rhythm is. And then they played these to a bunch of listeners, and the listeners had a little button they could press, and they recorded the times of the key presses. I forget exactly what the transducer was, but it was effectively the foot taps. And so then they have data on where people tap. So let me just show you that experiment, or something that is equivalent to that. So, yeah. So this is Sonic Visualizer, which is some software out of Queen Mary in London. And it does a lot of things. Very, very nice package for different ways of visualizing sound. One of the things you can do is you can make annotations just by pressing, in this case, the semicolon key. And so I can play this music and I can tap along and it'll record my tap times. I'll show you. So this is some choral music, I think. Okay, you get the idea. Spectrogram doesn't show so well here. It's a log frequency spectrogram, but you can see there's no percussion in this, right? It's just instruments. But you can sort of see what's going on. And then I was just pressing the semicolon key where I was hearing the beats, and here it is. It's layered them down. If we get it to play this again now, it'll. You can hear it's making little click sounds where I put my taps. So I put this together for a demo I did where I was actually trying to get people to collect this data live. So we can export this, and if we put it in the right place, then MATLAB will automatically find this, and then it'll plot this over the top. So what it's plotting here is for the 30 seconds of the excerpt. The blue dots are, each row of the blue dots is one of the listeners that McKinney and Mullens ran, and the dots are where they tapped, and then the red dots are where I just tapped on that. And then the black line down here is basically an average of all of those data. So you can see, I mean, they recorded 40 different tappers. And then I'm the 41st on here. And you can see there's a pretty good consistency among listeners of where they're tapping. And there are a few things to notice here. Firstly, there's a pretty good consistency, but of course it's not perfect, which you wouldn't expect, right? There's going to be some noise to do with exactly when people press and stuff. And then there are definitely idiosyncratic changes that some people are better at. Sort of, there's this interesting motor process that you couldn't press. If you hear something, you can't press it immediately. In fact, it takes you 100 or 200 milliseconds to react to something like that. But in music, you can anticipate when the next beat's going to be, so you can start compensating for that. Some people do that better than others. Like this guy here, you see, is consistently late compared to the average of the other people. Another thing to notice here is that there are different patterns, right? So I've actually sorted these according to the total density, total number of taps. And you see these people down here are tapping same as me, just once every, like that. But these people up here are going twice as fast. Because even though there's this sort of pulse in the music, you can imagine that there are intervening, I guess the actual melody that the singers are singing is there's sort of, there's eighth notes in there. So, or maybe even 16th notes. So you can hear the beats in between. Some people tap on that and some people don't. And so that's why it's important that they ran 40 subjects rather than just one or two, because it turns out there isn't a single right answer here. What there is a distribution over behaviors that our listeners will exhibit. And it's not clear how to, what you want your machine system to do. It would be kind of nice to have a machine system that correctly estimated these underlying probabilities, but then these things are not independent, right? It's like if you tap on the beats and not on the half beats, then you're going to do it consistently. It's not like you've got half the chance of tapping here as you do here. So the whole thing is pretty complicated, and we don't have a really good way of evaluating them. The actual scheme they used for Myrex for this evaluation was your system's output was graded for consistency with each individual person's output. And so you couldn't get 100% correct, right? Because if you only tap on these ones, you're going to miss these ones and vice versa. But you can at least get, you can try and agree with the majority. And there's a whole bunch of examples like that. So, I like this because, I really like this data because it's quite expensive and requires quite a lot of care to collect this data. But it really gets to the heart of these kind of music audio analysis problems, which is very often the problems we're interested in don't have hard, objective definitions. They're all about what people do, and then it's actually much harder to collect that and find out what's true. In the pitch tracking, very often you're trying to pick out the different notes. And then you say, well, maybe I've got a synthesizer, so I can actually record the MIDI events, when the keys were pressed. And so I know what the true notes are, and I can judge whether my system has correctly recovered those true notes. But even that sort of misses the point, which is what we care about is not whether you can correctly recover the underlying MIDI, but whether you can correctly identify what the listener hears. And there will be situations where those things are different, where the listeners may not actually hear all the notes that are being played anyway. But, then if you say that, then it becomes a much harder problem to say, well, what do we want to get out of this? Okay. So, as I said, there's been a fair number of systems of this kind. Back in the 1990s, I guess, were the first systems, and they would work from MIDI tracks, right? So you could have, say, a recording of someone playing a MIDI keyboard, playing some melody, and you'd have the set of individual note events, and you just have a bunch of time-stamped events. And even from that, it's not trivial to come up with a foot tapper, right? Because you say, well, some notes are going to be on the beat, and some are going to be in between, indicating the beat. And then since, 2000 or so, I guess from the mid-90s onwards, there are systems that just work straight from audio. So rather than assuming that they've got events marked already, they just look for some kind of change in the audio signal and mark that as an event. So typically you'll have some kind of front end to convert the audio into some indication of event times. And then you'll have some beat marking process, which typically relies on some kind of musical knowledge, more or less complex assumptions about what it means to be a beat sequence, like the beat sequence should be uniformly spaced, but maybe is allowed to get slower or faster at some rate. And then the output is a set of times of beats and maybe different levels of the metrical hierarchy, so the beat, the pulse, and then the bar lines or something like that. There are less detailed systems where the output is simply the tempo. So you just want to, like in a DJ application, you want to find all your tracks that are 130 BPM and group them together, so you don't really care where the beats are, you just want to know what the average tempo is. But then there are things like sometimes you want to be able to differentiate 3/4 and 4/4 type pieces and stuff like that, which generally comes from identifying where the downbeats are. And then this whole idea of like, okay, here's the fastest possible time division of notes, the pulse, the bars, and then maybe even phrases above that. So there's a whole hierarchy of subdivisions in our perception of rhythm. So let's talk about these pieces. We've got some music like this. This is the choral piece that we heard, Harnoncourt, and this is the maracatu, the percussion piece. And if we look at the spectrogram, in the maracatu, it's pretty obvious. We've got a bunch of these transient events here, which we see as these big broadband blips. In the the choral music, it's much less clear. There are no percussion events here, but there are definite points at which the signal gets louder because everyone comes in on the beginning of a new note. And so it seems natural that what we're looking for in terms of picking up the beats is looking for a big increase in energy, a sudden increase in the energy in the signal. And so we can do something fairly straightforward. We can define the energy of the signal as just the sum of the squares of the amplitude over with some time local window, right? If we just square the amplitude, we get a fairly rapidly changing signal, but if we smooth it with a local window, then we get an energy function. Another way we can do it is we can take the spectrogram, which already has something like this, but times e to the j omega, and we can just square each of those bins and sum them up. And we get, under the right conditions, we get the same thing. And so this is this is the square root of that, the sum of the absolute values of the individual spectrogram bins. And here you see for the drum music, there are these very, very dramatic spikes, which are pretty hard to miss. For the orchestral music, though, we still see there are these sort of points of big onset, which are where several parts of the spectrum change at once. You could think about weighting these by frequency. Right? For instance, you might think, okay, well, the transients often have energy in the high frequency, so let's emphasize the high frequency. So instead of just summing the magnitudes uniformly, we can weight them in proportion to frequency and get actually pretty similar results. These are probably a little more contrasty. This one looks pretty similar because there isn't actually that much difference between low and high frequency in forming this. And in theory, you could try and come up with a better set of weights, or even an adaptive set of weights that were somehow picking up on the particular characteristics of the track you're using, try and find the right places to listen to find the rhythm. One of the things that, just looking at the pure energy like that, one of the weaknesses is that often there's a huge imbalance in the energy in different frequency regions in an audio signal. Just because of the way sound is made, often there's much more energy in the lower frequencies than in the higher frequencies. And our ears have grown to work in those kinds of situations because we have a bunch of different frequency bands, right, that the cochlea is dividing up into. And then it's as if our sensitivity adapts independently in each of those bands. So that even though the energy in the low frequency, like in the 500 hertz band, might be 100 or 1,000 times louder than the energy in the very highest frequency band, because they're separate parts of the cochlea which can separately kind of adapt, you can be sensitive to both of those at the same time. So one of the things you might want to do is break your sound up into multiple frequency bands, and then have some kind of normalization that applies within those bands, and then sum up the onset indications within each of those bands separately. One way of doing normalization is to express the energy change as a ratio rather than as a fixed energy change. So rather than saying that the energy got louder by 10 units or something, you could say the energy got twice as loud in this band, or 4 times as loud over some time window. And then if the energy is very low to begin with, well, the ratio is the same versus if the energy is high, but it still gets twice as loud. So that's what this expression here is trying to do, it's saying we're going to take the energy at a particular frequency band at a particular time and divide it by the energy at that frequency band at the previous time. And then this ratio, if they're the same, then it'll be 1. If it's getting quieter, it'll be smaller than 1. If it's getting louder, it'll be larger than 1. So we'll subtract 1, so now if it's getting quieter, it's going to be negative. If it's getting louder, it's going to be positive. And then we'll clip it at 0. So if it's getting quieter, we just set it to 0. But now if it's getting louder, we get some value. And then the amount by, the proportion by which it's getting louder is now the value here. And then that's what we'll sum across frequency, with maybe some weighting function for different frequencies here. And this will adaptively weight the change in each frequency band by how much energy there is, so it's proportional to that. This has been implemented in PD using the bonk element from Miller-Puckett. And in the PD framework, he was just trying to put something together that would be useful for live experiments, live music performance, and would require relatively few tuning parameters. So this kind of self-weighting was successful for that. Here are our two examples, again, the Maracatu and the Harnoncourt. Under that, because we're taking now basically a derivative, right? We're looking at the difference between two adjacent frames, or the ratio between two adjacent frames. We see a lot more high-frequency stuff here. We see a lot more rapid variation. Again, in the drums, it's still pretty easy. But now there's rather more events going on here, although, the choral stuff is not terribly easy to use, to work with. Let me see if I can just show you that working. Is this going to play? Yeah. It's going to play, but not in a way that we can hear it. Let me just try that again. Sorry. Built-in output. Okay. What happened? Okay, don't know what's going on there. But this is how you use it. Here's bonk. It takes audio input, then it takes some messages for control, set a threshold. This is setting some thresholds for the onset, and then playing the audio, and then also seeing when this thing outputs a little event, a bang, every time it detects a pulse. I'm just using it here to generate a little blip, which you can't hear, but you can listen to it later if you want. Playing the Harnoncourt, it basically gets confused. You can adjust the thresholds to make it get different densities of events, but they're not at all rhythmic, right? It's not able to figure out that there's some longer term pattern going on here that it's supposed to pick up on. So one of the problems here is if you just look at the energy in a frequency band, then there can be sort of subtle changes, sort of things you can get with choral music, where the total energy is more or less the same, but because people are articulating a new note or something like that, or maybe there's a slight shift in the frequencies, the energy changes in such a way that if you're just looking at the average energy, you won't see much of a difference. But a listener who is listening to the whole signal can hear the difference. This is actually a little bit of a waveform, I think, of a cello solo. And this is like where they're sort of articulating by changing the bow direction. And what you see is like there's very little change in the waveform here, but there is very little change in the amplitude of the waveform, but there is this weird phase shift that suddenly it's like it shifts by a quarter of a phase cycle, something like that. And that's enough to indicate a new event, some kind of discontinuity in the waveform, which is what you can use to suggest a rhythmic event. So there's this very nice approach that was proposed by Juan Bello, who now teaches at NYU, and his collaborators, where, if we think about the complex energy in the frequency band, right? So in the spectrogram, we're just looking at the magnitude of the energy in each frequency band. But underlying that magnitude, there is underlying that frequency band, there is a magnitude and a phase. Now, normally, because the phase is relative to the analysis window, and like we saw with the phase vocoder, when you shift that along, the phase sort of changes in a systematic way, even for a fixed frequency sinusoid. So what you'd expect to see for every successive window is you see some kind of phase shift, which just depends on the relative size of the sinusoid and the window shift. So you don't necessarily know what it's going to be, but what you expect is going to be the same phase shift for every window. So if instead you get something which is way over here, well, the amplitude may be different from what you expected, but also the phase is a big change. And you'd like to be able to capture that kind of phase shift, even if there wasn't an amplitude shift, because you think it's relevant. And so their approach was, rather than just taking the magnitude or the magnitude difference or the magnitude ratio, they took a complex difference like this. And the complex difference is against a prediction of what it would be. So if this was x of, this was the complex value of the spectrum at time n minus 1, this is the value at time n, then we predict that at time n plus 1, it'll have the same phase advance and maybe the same magnitude change to be somewhere like this. And so if we did actually get something like this, we could take the difference between what we actually got in our prediction, and it'd be very small, meaning there wasn't any kind of significant onset. But if instead we get something like this, we can make this complex difference between them, and then take the magnitude of that as our onset strength. And then if the phase is right, but the magnitude is larger, then we still get some big difference. If the magnitude is the same, but the phase is different, we get a big difference. And if they're both different, we get an even bigger difference. So it's a nice way of having a measure that includes both magnitude changes and phase derivative discontinuities. And you can get it just like this. The prediction is that the magnitude is going to be what it was last time, multiplied by the complex ratio of how this time differed from last time. All right, so that's a set of different ways of just taking an audio signal and coming up with some kind of sequence, scalar sequence of how much onset or change or innovation there is in the signal, which is basically what we think. I mean, it's a pretty crude model, right? That we're saying, well, there's some audio, there's stuff changing in the audio, and then at the end of the day, we just have a single value, which is how large a change was there, and then we're looking for patterns in that change index with time that lead to rhythm. But that's a pretty successful approach. So now we've got this sort of time-based function telling us when things are changing. How are we going to actually find beats? Right? We can do what Bonk was doing, just say whenever it's large, we're going to say there's a beat, but they're not going to be regularly spaced. They're likely to be very irregularly spaced. And what we're looking for is something like what you get when you tap your foot, which is intrinsically something where you've got a regular pattern that repeats. So as I mentioned, the origins of this work, this work was from 1982, very early, which was taking, I don't even know where they got that data, because that predates MIDI, really. But they had some way of collecting actual timestamp data. Maybe they were doing it more, maybe it was, more theoretical. But they were trying to come up with a scheme for, like, how do you actually build something that will correctly infer the spacing between these temporal events to organize them into a regular pattern. And so they had these kind of grammar-type systems where you would have a sequence of symbols and ways of processing them to generate more organized symbols. And so this is a figure from their paper where they have a set of stages here which allow them to, take beat intervals and then update them and then maybe combine successive beat intervals or extend them, and then try and find the hypotheses that explain the sequence of intervals they saw. And of course, this is great grist for the mill of psychomusical experimentation, because you can make up arbitrary sequences of, patterns on some grid, beat patterns, then ask people what they hear, and then try and come up with a model that will correctly agree with what the people hear. The criticism of this is that, well, these arbitrary patterns are kind of not really stuff that you would encounter in music anyway, and so you're testing kind of the edge case rather than the general case of what really happens in music listening. But, you don't know where the answers are going to come from. You don't know what's going to reveal an important aspect. Through the 90s, there was more interest in trying to work directly from audio. And this piece of work was done by Eric Shirer, who was one of my colleagues when I was in grad school at MIT. And he was interested in this in the way that when you listen to a piece of rhythmic music, the sense of the rhythm builds up, right? That if you just hear 2 beats, you don't get a very strong sense of rhythm. But if you hear 4 regularly spaced beats, then by the end of it, you've got a pretty strong sense that something is going on. Even though, and also the fact that you don't necessarily have to hear every beat. Even if you hear 4 beats and there's one missing, you have this experience of where the beat would have been, this expectation. And so he was thinking about these sort of feedback filters where you have state that feeds back and loops around. And he was thinking that was a pretty nice model for what's going on with rhythm. So this is his rhythm tracker, and it's actually based on a pitch tracker framework, right? In a pitch tracker, you're looking for regular periodicity in the waveform, and some pitch trackers will try and do that independently in multiple frequency bands and then pool the results. And so this is like a pitch tracker, but working at 100 times lower frequencies. So now we're looking for periods of 1 to 2 hertz. But we break up the signal in different frequency bands. In each frequency bands, we have some kind of, just looking at the energy variation, we differentiate that to find the onsets in energy, throw away the negative values with a half-wave rectifier. But then we have a set of individual resonators tuned to every possible period over some range with some sampling density. And so they're like, they're comb filters, they're resonant filters with a particular period of sensitivity, which means that they're filters with a delay and then a feedback, so that any signal whose period matches that delay will reinforce, because it'll get when, at the same time as the last pulse is coming out at the end of the delay and getting fed back, the next pulse will be coming in, so they reinforce. So one of these resonant filter banks will be hopefully tuned to the period of the music of the sound that's coming in, and the rest will not. So you look at the total energy in the filter bank over all time, in the resonator, over the whole window, not just waiting for the pulse, but you say, what's the total amount of energy in the entire delay line? And then you have those for every possible period, and you got that set of periods for every frequency band, and you sum up all the corresponding periods across all the different frequency bands. You find the period that has the highest energy, and that gives you your tempo. This is just, at this point, it's just estimating, trying to figure out what the tempo pulse is. And it's kind of extravagant, right? Because we have, rather than having a system where we can look at the signal and just calculate the tempo, we're basically evaluating every possible tempo within every frequency band and summing them up. But it has this nice kind of, it's something you could imagine building in neural hardware or something. It's a very kind of hardware implementation-oriented view, and so it has this plausibility from a perceptual point of view. And it has this smooth behavior that doesn't suddenly change its mind. It's just like at certain points it may be that one period becomes stronger than another. And so you can see it sort of, you can understand what's happening even in terms of complex things like perceiving changes in rhythm. So this model has been pretty influential and seemed to make a lot of sense to a lot of people. At the same time, Masataka Goto, who is one of the very prominent researchers in music audio analysis, he was a graduate school in Japan, and he was putting together these much more computer science type approaches based on the idea that rhythm is ambiguous, as we've seen. His reaction to that was to say, well, what we need is sort of a multiple hypothesis system, a piece of software that's actually considering all these different hypotheses explicitly, having like little data records saying, well, this is this particular hypothesis I've got, here's my evidence, and then making decisions based on that. So he had this multi-agent system. The front end is pretty much the same, that you would have some kind of frequency analysis generating a bunch of onset times. But then he has some kind of routine which looks for time differences between onsets. And then if it sees one, it'll either generate a little tracker to see if there's more evidence for that, or it'll feed that into an existing tracker to reinforce it. And then some kind of global integration of that information to give the overall beat. One of the nice things about this is that you can put explicit rules or structures in this sort of integration stage to report multiple levels at once, right? You can say, well, if I see, three sets of strong periods that are subdivisions of one another, then maybe I can organize those into a hierarchy like this. He was not just trying to get out the tempo, he actually wanted to figure out where the beat was. He did all kinds of interesting things, including having like a sort of an animated computer graphics dancer that would listen to the music and move in time to the music. And he was also particularly looking at pop music, so he was able to take some kind of knowledge, like the fact that pop music has this typical 4/4 bass drum, snare drum alternation, and actually code that as prior information into the system, so it would automatically lock onto that and use that as its way of deciding where the downbeat was. So this is kind of consistent with the idea that downbeats are culturally determined, because he was using a template to find where the downbeats are. And there have been a bunch of systems like that. One of the most popular beat tracking systems at the moment comes from Simon Dixon at Queen Mary. He has a system called Beatroot, which is, again, sort of a multiple hypothesis, explicit tracking system. So when my lab started working in music in the mid-2000s, we were kind of late to that game. There were a lot of existing systems out there. But I developed a beat tracker, and the thing that was interesting to me was this idea of trying to figure out that the problem of defining the solution, right? So we can define the output as trying to agree with what a human generates, but what is the problem we're really trying to solve? In the terms of the Shira system and the Goto systems, there's an assumption that you're trying to find these regularly spaced sequences of events, because you're looking for a resonator, or you're looking for some kind of, you've got something explicitly looking for sets of events. And this sounded like a problem that you could actually optimize, that you could write down optimally. And then that's kind of nice from an engineering point of view, because then you can say, well, rather than having to build an algorithm that's just going to generate some sequence of events, I could say, well, here's the problem I'm trying to solve, and then the algorithm of how I find that is maybe a secondary issue, as long as I can say, well, this is whatever the algorithm is, this is what we're trying to optimize. So that's what this is trying to do here. It's the brace, the TI, the braces around TI indicate the set of times, TI for I equals 1 to n, or something like that. And then I'm defining a cost function over that set of times, set of beat times. And what we're trying to do is we're trying to maximize the value of some onset function at those times, right? Which is whatever it is. Our front end said, well, this point in time is showing strong evidence of having an onset, so we'd like to choose times that have that. And then we're simultaneously trying to optimize some function of the difference between successive times, right? So this is the idea that, well, what we're trying to do is find a set of times that are regularly spaced. So we want the difference between the two adjacent times to be some constant value. And this parameter, this objective function here, takes an optimal time, the tempo tau, as its parameter. And so for a certain set of times, given a tau p, I can calculate how strong the onsets are at each of those times and how consistent the difference between the successive times are with my tempo value. And then I can say, well, there's some set of times which maximizes that. There's some set of TIs that give me the largest possible value for that function. And that's what I'm looking for. So this tempo consistency function, basically, if the difference between two successive times was exactly tau p, then that's good. If it's to the extent that it differs from tau p, so the two beats aren't quite the period apart that I expect, then I want it to be to cost, to give me a negative score. So here is one possible example where I take the delta time, divide it by tau, and then take the log of that. If they're the same, then that'll be 1, so the log of it will be 0. If it's smaller, then it'll be some negative number. If it's larger, it'll be some positive number. So I square that to get an absolute value, then take a negative of that. So this thing is, in the best case, it's 0, and for any other value, it's negative. And so if we're trying to maximize C, then we want to keep these values as close to tau p as possible, these differences. So in general, this looks like something we could take any sequence of TI, and we could calculate this value for it. But, and we could at least notionally do that for all possible sequences of TI and find the one that scored best, but that's an awful lot of sequences, an exponentially sized search space. But the nice thing about structuring the problem this way is that we can use this recursive procedure of dynamic programming to solve it. So let's just see how that works. So dynamic programming is this funny algorithm with a long history. What's funny about it is that it's called dynamic programming for some kind of the guys who came up with the name. Boy, I should remember his name. Bell and somebody. They later were quoted as saying, we call it dynamic programming because they were kind of buzzwords at the time. It was like programming was very hot and we wanted to make it sound good, so we call it dynamic. But it's not really that descriptive of what's going on. But the idea is that there is a class of problems where there's an optimal solution, and the optimal solution involves solving a smaller problem optimally and then adding a bit on. But the adding a bit on doesn't alter the fact that the smaller problem is still optimally solved. And so then you can solve it recursively. You can break it down to the shortest part, solve that, which is typically easy, and then you can add on another step, and then using your previous optimal solution, extend it, and then keep going. So even though the problem solving the overall problem might be exponentially sized, because you can break it down this way, you can make it into a linear-sized problem, make the whole thing tractable. So dynamic programming is typically you're trying to find a minimum cost path through a set of assignments. It's often used for time alignment, and then it's called dynamic time warping. And so let's say we have some predefined starting point. We're trying to find the lowest cost path to some point out here. And we've got constraints on the paths. So let's say the paths, to get to this point here, we have to start from one of these 3 points. I mean, the constraints can vary by the task, but this is a common solution. So from any point, you can either move this way, or this way. And so there's still a lot of different paths we could go along to get to this point out here. Even with this grid of only 12 points, there are a number of different paths. But let's say if we're trying to figure out the best path up to here, well, we know that path is either going to come from one of these points. If we worked out the optimal paths, the optimal costs to each of these points, then we could figure out what the optimal path to this point was, because it's going to be whatever the cost was to these ones, plus the added cost of moving to this point here. And so typically these costs will involve a local match, which is like, well, how, if you're trying to align two sequences, do these local points line up at all well? It's going to be the local cost, which doesn't, it's going to be the same for any of these previous paths. But then we're going to look at all the possible preceding points. There's going to be maybe there's some transition cost, which says, well, if you want to go diagonally, then that's got a certain cost associated with it, versus if you go vertically or horizontally, that's got different costs associated with it. But at this point, if we know all of these things, then we can work out all of these costs. And then we just simply choose the smallest one. So we have a very simple decision to decide which one of these to choose. So we've done that there, but we've sort of done that progressively all the way along. For every point on this grid, we've found out what the best previous point was. And then when we evaluated we sort of started down here, worked out for each of these points what the best preceding point was. And then at the end, you get to some point, and you can follow this list of best preceding points, and you get the best path. Right? So you've actually solved the minimum cost to all the points on your grid, the minimum cost path. And it's just taken you, for each point, you've had to examine some small fixed number of preceding points, but that's it. So it's just the complexity of the problem is just the number of frames and the input and the reference thing. It's order n times m rather than some exponentially sized problem. And the key thing here is that when we decided what the best path was to get to here, whatever happens subsequent to here doesn't alter the cost of getting in here. It's only subsequent stuff that makes a difference, which is called these optimal substructure problems or submodular problems, where you can break down, compared to well, we'll talk about that in a second, like what the problems that don't have this property. But so on the previous slide, this problem does have that property in that, once I've got a set of times, then I can calculate the onset cost and the tempo consistency for all those times. And if I want to add another point time on the end, well, I'm going to have to add a new one of these onto here, and I'm going to have to add a new one of these onto here, but it's not going to affect the values of all the points up to there. So it has this optimal substructure property. Now, the thing that's the biggest drawback of this approach is that we had to know this tempo ahead of time, right? Which in general you don't know, and the listener certainly doesn't know when they start listening to something what the tempo is. So this is like this unrealistic part of the problem. Now you can imagine if you were if you're listening to a series of events, you maybe have some expectation of tempo because you decided that your set of events are in a sequence, and so the spacing between them is a tempo you expect. But that tempo might adjust as you get more events and you listen to them. Now that would be a situation where the optimal substructure doesn't hold, because if you change this, then suddenly the total cost of all your preceding events changes, and now what may have been the best set of events up until some time would no longer necessarily be the best set of events if you change this. So this whole approach requires knowing the tempo ahead of time and having it fixed throughout the whole track, which is the secret to making it that we can find the optimal solution, the globally optimal solution using this approach. But so it's sort of, from my point of view, it's worth it because it makes it into a very nice problem. But if you don't have a good way of getting the tempo, or if you don't have a constant tempo, then you're in trouble. So how do I solve this? Well, tempo is a little easier to find than the beats because it's more of a global property. And so what I do is I have a first stage which estimates the tempo and then uses that to feed the beat tracking. And what the first stage does is it just takes has some function for generating the onset envelope, right, which is looking at just the differences in energy. And the idea is if you have some period, which is the tempo, then that's going to be a regularly spaced set of regularly spaced pulses. So we can reveal that kind of thing with autocorrelation. So if we just autocorrelate this onset envelope, we get something like this, and we do see these regularly spaced beats coming out pretty clearly. I'm not sure what signal this was, but this is typical. I mean, for a music signal with a strong beat, you're typically going to see an autocorrelation like this. So that's pretty easy. We just take one of these peaks as the period. The only problem now is deciding which peak to take. And obviously, there's always going to be a peak at 0, but that doesn't mean anything. That's just the nature of autocorrelation. So it's going to be one of these peaks away from 0. But here we see, well, there's this one, and then, there are a bunch of others out here. So I was actually designing this system to try and agree with that human data, the McKinney and Malentz data. And so I could calculate for each of those human tapping records, I could calculate the tempo, which was just taking the difference between successive taps and taking the median of that across the whole track and using that as their reported tempo. Then I could take that for all the data they had. So they have like these 30 different tracks, all at different tempos, but sometimes people tap twice as fast. I could build a histogram of that, and that gave me a sort of a profile of the human tendency to tap, that people are not going to tap at 20 beats per minute. They're not going to tap at 300 beats per minute. There's something in the middle where they're going to tap. And in fact, it turned out to be pretty much a nice Gaussian, centered at 120 beats per minute, a Gaussian in a log-spaced domain, so that it seemed, from that data, it seemed like the average tapping speed is 120 beats per minute, but you're equally likely to tap at 60 and 240, so same ratio apart. When you take that log domain tempo Gaussian and plot it on the linear period here, you get this log Gaussian, log normal distribution like this. And so what I did, I took the raw autocorrelation, just scaled it by this log normal tendency, and then took the highest peak there. Now in this case, it's this one here. Because as we saw, the data involved people sometimes tapping slower, sometimes tapping faster, the system also tried to estimate a secondary tempo, and it looks for a peak either 2 or 3 times longer than this first tempo, depending on whether it's 2 time or 3 time. So here it's found a secondary peak at twice that. Is that twice? Yeah, at twice this tempo here, which is going to be the slower beat. But notice that the actual pulses here are spaced at half this period, but it's ignoring these odd-numbered pulses and just going for this second beat, because that's here, 0.5 seconds is 120 BPM, so this is already a little bit faster than that. It's like 150 or something. So this, which would be like 300 BPM, is too fast for anyone to plausibly tap at. So we do this on the first 30 seconds of the audio, some big chunk of audio, calculate autocorrelation, find the peaks, and then that gives us our tempo. And from then on in, we can run the dynamic programming to find the optimal set of beat times. So here's how the beat estimation part works. This is our function, right? We're trying to calculate the sum of the onset values at the times and the sum of these tempo consistency terms. And we can do it recursively. So we're trying to, at every time, we're saying, well, what's the best sequence of beat times that includes a beat at this particular time? And we call that C star of t, right? So it's a function that has a value at every possible time, and it's the best cost up to this time. And we're saying, well, this is like the best cost to some particular point on the grid in the dynamic programming grid. It's going to be the local cost here, the value of the onset function. So here's the onset function. And then here is our search over the preceding sequences. But now it's not just 3 points, but it's like some window of possible times. So the max over the preceding time of the tempo consistency, if we have a beat at this time and we have a beat at that preceding time, and the best cost of all the best sequence cost of sequences that ended at this preceding time tau. So here's our onset function. Here's the time we're looking at. And here's our C star, our best cost of all sequences ending at this time for every possible time. And so we're looking back at different time taus back here. We're taking the value of our C star here, right? And then we're also taking the value of this tempo weighting function, which you remember is a squared and the negative of some log ratio squared. So it's like a negative parabola, skewed parabola on a log axis, but it's like this. And then there's this alpha term which balances those. So we're just looking for the time tau that maximizes the sum of the green and the red. And the red stays the same, and the green is what we calculated already. So you can sort of see that the sum, we're looking for a point that's a local maximum in the green. There's a little bit of bias that the red can add to us to try and choose the one that's closest to our tempo window. Like, so ignore these ones because they're not the right number of beats, but this one's about the right place. And so and that's, you can just calculate this moving forward. Every time you look around and you calculate it, update your C star, and when you get to the end, you have to choose some local peak in your C star function. You don't want to backtrace from here. Once you've got a local peak, then you just, as long as you've stored what your tau was at every time, then you can just do a backtrace and you get your beat sequence. So that sort of makes sense, right? It's not exactly traditional dynamic programming, but it's the same idea. And when you write this in MATLAB, this ends up being a very, very simple function in MATLAB. So this is my implementation of that in MATLAB. The green is just comments. The black is the actual stuff. We have an array which is the backlink, so we can find the preceding beats. Have an array which is the cumulated score, the C star, which we initialize with the local score, just the onset function. Then we have to have the period as an input here. And then we have a search range, which is basically, these are all the possible values, all the preceding periods we're going to consider. And we do it from twice the period to half the period, right? Because outside that range, the parabola is going to be too large. And then we have the transition cost of choosing any of those points, which is to do with the values here divided as a ratio of the period, the log of that, and the square of that, right? Multiplied by alpha. These values are all negative because I'm going to add them on. So I divide it by the negative of the period just to make sure these values I'm taking logs of remain positive. So once I've set that up, then all I do is I just take the, basically every point here up to the end of the local score. I get my range of preceding points I'm going to look at, which is where I'm looking at, plus this range of preceding points here. So this is now a vector of values. I calculate the total cost each of those points would occur as the transition cost from here plus the preceding cost up to here, because these values are all negative, so the values are already calculated. Now I've got a vector of the total costs for each of my possible preceding periods. I just find the maximum of those, the value and the index, which is what I care about. The current total score becomes that value plus the local score. Actually, I guess that's kind of redundant with this. I didn't have to initialize this. That sort of comes for free. Or it could have just, if MATLAB had a plus equals, I would just plus equals the VV onto this. And then I remember the time at which the actual preceding point, the best preceding point was by taking this XX and indexing my time range with that. And that just gives me my best score. So I just loop through this every time. The only work is here in max. Max is telling me what the value was and where that value occurred. And that's automatically finding the best possible preceding value. Do that for every time. Then at the end, I just look at the largest value of my cumulative score, assuming the score keeps going up because the transition cost, the local onset function is, I'm having some positive values in here. So this is going to be one of the last beats is going to be the time that gives me the largest total score. And then I just work backwards, looking at the backlink for that beat and working the list backwards until I get to a time whose preceding link is 0, meaning it's the earliest one in the chain. And that's my result. I return it back. So this is kind of, this is kind of the, if you like, the magic of dynamic programming. But it solves this problem without, it's like, well, wait, where do we actually solve the problem? But it sort of, it does it for you. Here are some results of running this on a couple of examples. These are some of the other examples from the Merlentz data, McKinney-Merlentz data. Bonus 1. Another choral data, another choral example like that. And then bonus 6. Which has, drums, is pretty straightforward. What we're plotting here is the output BPM, again, just calculated as the median of the time differences between the emitted beats, versus the target BPM, the actual tempo that I put in as the tau value, right? And so what we're seeing here is that, well, and this is the so-called, the correct value is somewhere in here in the middle. And I've got two different values for alpha, which is the weighting function, the balance function between weighting the local onset function and weighting the tempo score function. And so the point is that the actual input tempo doesn't have to be exactly right. There's some range of values in here where it doesn't matter what you set it to, it's still going to find the same sequence of beats. But if you set it, twice as fast, then it's going to lock on, and these different functions out here, it will lock onto them. And it's showing that as you increase the weighting of the tempo function, it's going to be more likely to look at the right, to try and find things that are consistent with the tempo rather than worrying about finding the best local beat strength. There's not a lot of variation with alpha. The message here was there's this tuning parameter alpha, but it doesn't actually have that much influence, so it's not such a big deal. Here's the actual accuracy, how many of these beats are agreed with the ground truth. Here I filtered the ground truth so that it was only a single metrical level, so that the peak result was 100%. And it shows that over this range of about 10% variation in tempo, the system is picking up all the right beats, but if you get the tempo wrong, if you get the initialization tempo wrong, then it drops down, obviously. And here's a measure of the stability of it. The standard deviation of the interbeat interval is divided by the mean. And so it's saying that here we're down around 5% fluctuation. And as you increase the tempo weight, that gets a little better. The spacing becomes a little more rigid. But again, it's not that variable. So it works pretty well for this choral piece, which has no well-defined beat. And here for the jazz piece, it's even better. There's a very nice beat, and it's getting fairly low accuracies, fairly low drifts, jitter, and pretty high accuracies. Yeah.
How does the actual music sound when the accuracy was really high? Was it so that's straight from the song that you just played, right?
Yeah.
And so basically you said the accuracy ranges from 0 to 100%.
Yeah.
And there's a part where it's super accurate.
Right. So these here, I'm sort of saying, I got the tempo. Basically, it's as if I got the tempo estimate totally wrong. And so what happened? And what's going to happen is the tempo is saying, it's it's actually at 100, and it's actually at 90 BPM or something, but I'm looking for it at 40 BPM. It's going to miss every other beat, something like that. So it's going to find some kind of consistent sequence of beats, particularly if it's like a factor of 2. It'll pick every other one, but for the scoring here, we've said, no, you've got to get every one. And so it's, you lose. But it raises an interesting point, which is that, okay, to do this scoring, I had to choose a single metrical level. And it's very easy for me to, with the pulse thing, to get a rapid pulse, right? But sometimes it's like, no, you want the dun, you want the slow pulse. And then there's this risk that it's going to choose the offbeats. So it's going to, the thing should be like this, but the thing's going to choose them at the right spacing, but on the offbeats. Then you get 0% correct, because like, you've got the right number of beats out, but they're all exactly 50% off from where they should be. And it turns out that as you try and track it lower, and you could say, well, okay, you could say, okay, this is 120 BPM music, and I'm trying to track everyone. Or you could say, no, there's a slower pulse at 60 BPM, and then you get different kinds of failures, right? It might just fail to find the right times, or it might lock on to the ones that are out of phase. And so with this system, you're better off looking for a faster pulse where you're going to get every single one, and then worrying about dividing it down to lower levels, lower metrical levels at a subsequent stage, because it's not very good for differentiating between downbeats and upbeats, the things in between downbeats. So, yeah, I mean, that's the next thing, is this idea of trying to find these downbeats. And like I said, Goto's approach was to just assume that we're looking for some kind of particular arrangement of drums. So it'd look for like a low-frequency drum at the beginning of the bar. And Tristan Jahan's approach was to basically say, well, give me some examples of music where you've got the downbeat marked, and I will just train a machine learning system to figure out, what the appropriate features are that tell me where the downbeat are, and they could be anything. They could be low frequency, or they could be something else, but it'll just, there's no way of knowing them without someone showing you what the examples are. So that's it. We have this issue, we have this phenomenon of rhythm perception. Not sure where it comes from, but it's very essential to a lot of different kinds of music, and it has this hierarchical structure. When we're trying to build computer models of this, there are these things. It's got a slightly longer timescale than the music itself. That the perception of rhythm builds up, perception of rhythm persists even if the music starts to do something different. So we want something with some sluggishness, some inertia in it. And then I described in some detail my particular approach using dynamic programming, which has this really nice property that we can say we found an optimal solution, at least to the reduced problem that we solved, although in order to do that we had to deal with this idea of estimating tempo ahead of time. There are a bunch of different ways of extending this to try and deal with the fact that some music does have varying tempo. Clearly listeners have no trouble with that. But there isn't such a clean, optimal solution that I've come up with for that. Okay, any questions about that? So on Wednesday, we'll be working in MATLAB, and we'll be running some versions of that little beat tracking system that I just showed you.